Hi, in today's screencast, I'd like to go over some analytical methods that we will see used in the different papers that you will be reading as well as in lectures, so we're familiar with the different mathematical and statistical methods that are used to measure some of the parameters we've been talking about in lecture and in the previous screencasts. And essentially, the three parameters that we are concerned about are period, phase, and amplitude. And for different reasons, sometimes you will be interested in one but not on the other. And as we'll see, the methods to measure one are very different to the methods to measure the other. So let's say that we're interested in period, and actually I already talked briefly about how to measure period, and indeed you will see these in the Johnson paper that you will be discussing on this Friday. That is the first discussion section of the quarter. So if you have an actogram with a clear activity onset, and in this case this is running wheel in a hamster, and this is a double plotted actogram. Forget about this. This animal is under entrainment, but it doesn't really matter. We'll talk about that later. But the point is here that we have a very clear bout of activity. This is a double plotted actogram. So remember, we have day 1 here, and then day 1 here replotted, then day 2, and day 2 replotted, and so on, right? So you have a 48-hour span, so you can visualize nicely this bout of activity that spans through the 24-hour window. So in this case, because hamsters have a very accurate circadian system, particularly when you provide a wheel, it's very easy to trace this line through the onsets of activity. Here you can see this black line that I'm going to highlight in blue that we traced, and in fact, this is the same bout, right, but without the line, so you can have a feeling of what the raw data looks like. And then what you do, as we talked about, and as you will see in the Johnson paper discussed this Friday, you essentially what you do is you plot the time deviation in hours versus the days, right? So basically what you do is that you plot the time deviation of hours from the 24-hour period. So in other words, how different on each day is the period from 24 hours. So for instance, from day 1 to day 2, let's say that you go from if this is the 24-hour mark, this would be minus something like 30 minutes. So basically your time deviation from day 1 to day 2 would be 30 minutes, from day 2 to day 3 it would be maybe an hour, and so on. So you plot those dots, and then basically what you do is you fit the best fitting curve, and you use typically regression analysis to do this. And that's a statistical method that allows you to tell what is the best fitting line for this cloud of points, okay? And then you can calculate the slope of that line, and what that slope means is how much does the period of this animal deviate from 24 hours on successive days. So if the slope is, in this case it's negative, let's say that slope is minus 0.5 hours, that means that the period of this animal is actually, or the tau, is actually 23.5. If you have an animal that has a longer period, right, with an actogram that would drift, let's say, if the actogram looks like this, with the bouts of activity drifting to the right, that is a longer period than 24, then when you do this analysis, the slope will be positive, and then when you measure that slope, that deviation will give you a period that will be larger than 24 hours. Okay? So essentially, that's a very easy and intuitive method to calculate period based on the actogram. Sometimes the problem is that you don't have very clear bouts of activity. This is data from a rat, and this is with infrared detectors instead of a running wheel, so it's typically noisier. But what I mean by noisier is that you can sort of see that this animal has a period that is longer than 24 hours, right? Again, this is double plotted, so it goes from 0 to 24 to 48 hours. And these are days. But if I tell you, can you trace a line through the answer or through some, it'll be hard. Some of you could say, well, it's here. Some of you could say it's here. So it's a little bit dirtier. So what do you do when you have dirtier data like this? Well, there are statistical methods and mathematical methods that allow you to extract the period out of this kind of noisy data. And this is one method that uses the variance of the data across time, so how variable the data is. And this is called the periodogram, and the way it works is, imagine that now you plot your data in linear time, right, as we've seen before, right? And this would be kind of a sinusoid. And basically what I'm drawing here is how this oscillation changes across time, right? So this would be time and variable A, whatever we're plotting. And what you see below here in gray shadings is the data represented, instead of in real numbers, in color intensity. So the darker the gray, the higher the value, okay? Just graphically. And then what the method does is it takes several days. In this case, I'm only showing 3 days. So I imagine that you have a month worth of data, and it chops the data into different chunks of different times. So for instance, in this case, the chopping is done every 6 hours, right? So basically, you take this block of time and you put it here, and then you take this block of time and you put it there, and then you take this block of time and you put it there, and so on. Okay, and then you take, in the next stage, you do exactly the same with the very same data, but now the block size is, instead of 6, in this case it's 10 hours. Okay, so basically you take now this block of time, okay, and you put it here, then you take this block of time and you put it there, and so on. And then you keep doing this for increasing intervals. So you do it for 6 hours, for 10 hours, for 14 hours, for 18 hours. You can step up or in any amount. You could do every 2 hours increases or every 4-hour increases. And basically what you have here is what you ended up when you lined up the very same data in different intervals, right? And then what the method does, it's quite smart. It calculates the mean color, if you want, that you get for each one of these blocks, okay? But particularly, the most important thing, it also calculates the variance for each block. So in other words, what was the variance here? What was the variance here? What was the variance here? And so on, okay? And then it calculates sort of an average variance. okay, for all the blocks. And it does the same here, calculates the variance here, and so on, and then it does the same thing here, okay? If you look at this data, what really comes out is that, let me just erase this. So if you now think about the different colors that you have represented in each of the blocks under the different intervals, what you can see very clearly is that um, when you choose oscillations that do not coincide with the main oscillation, if you think about the period here, okay, the period that I draw here in the linear time corresponds to, again, goes like that. This period corresponds to 24 hours, right? So whenever I line up the data in intervals that are very different from 24 hours, like here or here, what you can see is that the variance for each block will be very low. And the reason for that is that here you will only have white and gray. Here you have darker grays. Here you have also white and light gray, and so on. However, if you go to the 24-hour block, you can see that within the same block, you have all the colors represented, meaning that this is high variance, right? Whereas this would be low variance, okay? So what follows from this rationale is that whenever you happen to hit the period of the oscillation that you have, you will have an increase in variance, in the variance that we calculate. So without knowing the period, what you do is you do this for many intervals, right? And this is an example here. This is time now. Again, we have an actogram. And by the way, the period in this actogram is 22 hours. And I know that because we've done the analysis. And what you plot is variance. This is variance versus the time at which you split the blocks. So this would be blocks of, say, 15 hours, blocks of 16 hours, blocks of 17, so on. And then what will happen is that whenever you hit 22, because this period is 22, you will get a very huge peak in variance. So this increased variance means that your oscillation, whatever you were measuring here, has a period of, in this case, 22 hours. It's in minutes, okay? But if you translate that to hours, it will be exactly 22 hours. So, in other words, without knowing the period of this oscillation in a very noisy data set, you can extract the period very nicely by applying this periodogram analysis. And you can see, the other thing that you can see in this plot is that the method is designed in such a way that you can tell whether the oscillations are truly statistically significant. And this line here is the significance line. In this case is with a p-value of 0.05, which means that any peak that goes above that line, you know that is statistically significant with this p-value, and it's indicating that that period is really the period at which your variable, your biological variable, is oscillating at. By the way, you could use any of these methods for any oscillatory data. For instance, people calculate the stock market cycles this way, so you use similar analysis to see whether there are patterns in cyclicity when stocks go up or go down. So you can use these for any data, not just biological data. Another method that is used to estimate period is the fast Fourier transform. And the idea behind this method is that any complex signal can be deconstructed into a summation of sinusoidal waves. So imagine that you have a very nice oscillation in linear time again. So this is time and the value of your variable. And then you know that this period, let's say, is 23 hours. So if you measure from here to here, let's say, it's 23 hours. And you know that it's a very accurate oscillation, so the period is exactly 24 hours. And then I tell you, I want you to plot me, to use this data to construct the following plot. Plot me amplitude of the oscillation, and usually this is referred to as power. Power is an indirect measure of how wide this oscillation is, right? As a function of period. So this oscillation has 23 hours, so I tell you, and I want you to do this for periods that range between 15 hours and 25 hours, let's say. Okay, so then what you do is, well, what is the amplitude of oscillations that oscillate at 16, let's say? And you can see here that there's no oscillations oscillating at 16, right? So basically this would be very close to 0. Then you go to 17, also close to 0, 18, also close to 0, 19, and so on, until you will get to the point where it's 23, right? And this is the period that I told you that the oscillation has. And of course there you will have a very large amplitude, because you know that this oscillation with a 23-hour period is very prominent, okay? Sometimes instead of period you will plot frequency here, so it will be one cycle per X amount of time. Remember that period is the inverse of frequency, but the point is exactly the same. What you will do is then you will merge these points, and in this case, where you have a very accurate oscillation with a 23-hour period, you will see only a peak at 23 hours, right? So let's see now another example. Let's say that instead of an oscillation that has a 23-hour period, you have a little bit noisier oscillation that it's mainly made of two overlapped biological oscillations. So now we have, again, time and the value of your variable A. And now the oscillation looks like this. There is a high amplitude oscillation with a 23-hour period like before, but then overlap to it, there's a lower amplitude oscillation that looks like this. So then the period of the longer period oscillation is 23 again hours, but the period of this one here, let's say, is something like 3 hours. You know, this is not scale, I'm just making this up. And then I ask you, can you please do the same exercise as you did before, but now I want you to plot the data between 1 hour and 25 hours. So again, we have amplitude or power versus periods. And then basically what you will get here is, if this is 0, 1, 2, 3 hours, right? And you get up to 25 here, what you will get is that this will be very low, then you'll have a relatively small peak here at 3 because the amplitude of this 3-hour oscillation is relatively small, and then it will go down, right? Stay down here, and then when you're close to 23, you will see a bigger peak because these peaks are proportional to the amplitude of each oscillation. So you can see that the 23-hour oscillation has a very large amplitude, whereas the 3-hour oscillation has a very small amplitude. Okay, so basically, what this FFT of this signal will look like will be something like this. Okay. And the idea is that these are very simple oscillations that you typically will not find in biological systems. But if you have more noisier oscillations, the analysis will look something like this. So here's a hamster. In this case, it's a hamster that received a transplant of the suprachiasmatic nucleus. We'll talk about that later. But the point in this case is that in this hamster, you have multiple oscillations. You have one oscillation that seems to be close to 24 hours, and another oscillation that it's slightly shorter, and maybe even high frequency oscillations. So basically, when you do these, you get a much more complex FFT, okay, that looks like this. It's not as simple as the case that I presented before, right? Remember, in this case, we have an actogram, right? But if you were to plot this in linear time, this would look something like this. Every 24 hours, you'd see a little peak, and then another peak, and maybe every 22 hours, you'd have other peaks that are represented here. The point is that when you have a signal that on linear time or in actogram form looks relatively noisy, you'll get many components, many frequency components or period components. In this case, the biggest ones are one that has a 24-hour rhythmicity period, and the other one that has a 21.8-hour period. Okay? This type of analysis, the FFT, is very much used in electroencephalographic recordings, and we'll see that when we start talking more about sleep analysis, that in fact it's very convenient when you have, for instance, an electroencephalographic recording that looks like this. Well, then, if I ask you what's the period or what's the frequency here, it's virtually impossible to know that, right? So, well, if you apply the FFT, you can deconstruct this signal to something that looks, again, like this, with one single peak and maybe another peak, and then you can tell me, well, I see a peak at this frequency and another peak at this frequency, or a peak at this period and a peak at this other period. And the FFT becomes kind of a signature of signals that are very complex, that by looking at it, it becomes much easier to visualize what periods, what frequencies are represented at there. So far we talked about period. What about phase? Well, phase, I told you there's one method that is used typically, which is, if you have an actogram and you have bouts of activity like this, and suddenly that bout occurs later on a given day, then you can calculate by extrapolating in the same way that you do for period. You extrapolate the onsets of activity back to the previous day that you apply this treatment, and then you can tell me if I measure the difference between this line and the difference between and the line before, then that will give you how big the phase shift is, or phi. So in this case, we know that this is a delay, right? Typically, we measure delays with negative signs. This is a convention. And then if instead you have an actogram that does this, and I'm not putting the units now, I'm just simplifying it, so that the onset was here and now it's here, that would be an advance. And again, in this case, you define that as a positive number. And it's, in this case, it's defined in phase. There are other methods that that can also be used in phase estimation. So I'm not talking about amplitude estimation yet, okay? I'm talking about phase, okay? I just didn't have a blank page. So for amplitude estimation, for phase estimation, you can also, if you have in linear time a complex signal, let's say that looks like this, and then another signal that it's, say, something like that, and I ask you, well, is the phase difference, what is the phase difference between these two signals? And again, this is, let's say, signal B and signal A versus time. So how do you know what's the difference in timing between those two cycles? Well, one method, what it does is it fits a cosine wave, the best fitting cosine wave, and again you use mathematical and statistical methods to know which is the best fitting cosine wave to the blue signal, and then you do the same with the red signal. You fit the best fitting cosine wave, okay, and then you take, say, the peak of that cosine wave and the peak of the other cosine wave, and you say, okay, the difference between the two peaks is 2 or 3 hours, whatever, and then that's the phase difference between the two signals. So this method is called cosiner, and you will see it in some of the papers. So now we go to amplitude. I told you that for amplitude, as opposed to period and phase, the actogram is not a very good method to determine amplitude changes. And the reason for that is that in the actogram, the real values of activity or temperature or whatever you're measuring are compressed very much. So what I'm saying is, let's say that on a single day, your activity looks like this, okay, whereas this, where this is night and day. It's not working really well. Okay, night and day. Well, on a single day, I can visualize the amplitude very well, right? But then when I transform this into many, many days and into an actogram, right, this is going to look like, day 1 it's going to be like this, and then day 2 it's going to be like that, and day 3 it's going to be like that, and therefore it's very hard to visualize how much amplitude you have each day. So how do you look at amplitude in general? Well, there's one method that is called a waveform, and as its name indicates, it's the form of the wave of whatever you're measuring. And the way it works is, imagine that now you have that same set of data. Oops, sorry. Now in an actogram form. Okay. So basically this is days, and this goes from 0 to 24 hours. And then, this is activity in a human being that it's under a light dark schedule that looks like this. So this is dark, and this is light, and then on day one you have this kind of activity, and then on day two, for some reason, this person went up a little, got up a little bit later. On day three, like that, and on day four, and so on. There's a weekend here, so it's much later. And let's say that you have these bouts of activity through many, many days, and I ask you, well, can you tell me what's the profile of activity of this person? What is the general amplitude of the activity profile? Well, you may say, well, it depends on which day you look at, but another way to look at this is, well, maybe what I can do is I can give you a typical profile of this person based on all the days that I recorded from, okay? And in order to do that, what I'm going to do is I'm going to create another plot, and that plot is called the waveform, okay, where I will also have 0 to 24 hours, but instead of plotting just a single day, I will plot hourly for it, say hour 1, hour 2, all the way up to 24, how much activity, the average activity for the first hour of all the days taken together. So let's say for hour 1, which is, the start of the night, there was very little activity. Then for hour 2, there was a little bit less, let's say. Hour 3, a little bit more. I mean, let's imagine that there was some activity. So essentially, you will get averages that will be like this, okay? And then suddenly you get into the morning here, and if you take this hour here, right, there may be some activity there. A little bit later, there's going to be a little bit more because the average will grab more activity bouts, and so on. As you keep averaging this activity, you will get something like this. And then it will go down again, okay? And the good thing about this is if you have enough days that you recorded from, not only you can get the mean, but you can also get the variability. So you could plot mean plus standard deviation, which is a measurement of variability, and what that information gives you is how variable the activity was for, say, 9 a.m., right? Or for 6 a.m., if 6 a.m. is right there, right? And so on. So basically, what you get out of these waveforms are plots that look like this. If this is now the light-dark cycle, and this is a representative light-dark cycle, it's not a single day. Basically, now I'm plotting the morning here, and the light here, and the dark here, right? Basically, what you see for a typical human being is, high activity here, maybe a little bit higher here, maybe around here a little bit less, and I'm putting those bars represent the standard error. Then, you typically at noon, activity goes down a little bit. I don't know, if this person every single day sleeps a nap, you may have a low of activity in the middle of the day, and then it goes up again. And then if this person typically stays up into the evening, late hours, you may get something like that, still activity during the night, okay? And eventually, this person goes to sleep for the nocturnal sleep, and you get something like that. And essentially, when you merge these points, what you get is the typical pattern or profile of activity for this person based on the days that you measure. And of course, you can do this for a plant, for an animal, for any kind of organism that you can measure successive days of whatever you're interested in. And of course, this is very helpful because it gives you not only a good sense of what the amplitude is, but also gives you a good sense of what the typical profile of activity of this person is. For instance, you could have in the same plot, sorry, I forgot this time here, in the same plot, you could have so this is the person in black. I'm going to draw another person in red. You could have in the same plot somebody that doesn't sleep a nap, for instance, and the plot would be something like this. And I don't know, maybe here there's more activity, here there's less, and then if this person doesn't sleep a nap, it may go to bed a little bit earlier than the other person. But if you overlap the two waveforms, you could have a sense of how different the profile of activity is between these two people. So that's as for amplitude and waveform, and this is essentially, the most of the analysis that you will see in papers and lectures. If we have any other new kind of analysis, we will give you that information beforehand. But with this, you should have the basics for data analytics, and we'll have a quiz on this on Monday, April, let's see, 3rd. So, and I'll post this on the announcements. Thank you.